Welcome back to another video. In this episode, we are going to look at how we can handle problems on uh, eigenvalues and eigenvectors when we are interested in finding the diagonal matrix, right? So, for instance, when you have a matrix A given its eigenvalues and eigenvectors, and you want to check if this particular matrix is indeed can be diagonalized, right? Indeed can be diagonalized. What you have to do first is take this matrix A and check if you can find its diagonal matrix for it. Okay, so how do we do that? We have an equation, well-known equation for it, right? So that is A equals P times D times P inverse. Okay, so this is the equation that we use to find or check if a matrix is diagonalizable. Okay, so we don't change the position of these matrices, right? Basically, they are matrices. Okay, so P times D, D is the diagonalizable matrix. Okay, so and P inverse is the inverse of P, right? So here, the moment you change P, the position of P and P inverse, you're going to have a different thing altogether. Don't forget that P times P inverse is equal to an identity matrix. So once you have P inverse D, this is a different thing altogether. This changes to D, and this is not the same as this, right? So never ever write it in this form. It is in this form. And two, don't forget that matrix multiplication is not commutative. And as well, matrix respect order. So once you change the position of P and P inverse, or D and P inverse, or D and P, you are going to have a different result altogether. So always you have to quote this equation: A equals P times D times P inverse. Okay, so what does this P, D, and P inverse mean? So here, our A has been given, right? Our A has been given. That is the matrix. That is the matrix, right? So here, the P is the eigenvalues that we have been given, the eigenvectors that we have been given. So the P here denotes the eigenvectors. Okay, so the eigenvectors represent the P, right? So you're going to combine the first eigenvector and the second eigenvector, and that becomes your matrix P. So you combine the eigenvector 1 and eigenvector 2, and that becomes your P, the matrix P. Okay, so we have 1, 1, 1, neg 4. So this becomes your matrix P. So now you have A, you have P. What is D? D is what you are interested in, right? So you have to find the P inverse as well. Once you have the P, you can find P inverse, right? So here we find the P inverse, and once you are interested in P inverse, means you need the determinant. Once you find the determinant and it's not equal to 0, it means the inverse of P exists, right? So we're going to find the determinant of P right here, and that is equal to negative 4 times 1, negative 4, 1 times 1 is 1. But off diagonal, we take negative, so it's going to be minus 1. So that is going to be negative 5. Okay, so we have the determinant of P. We need the inverse, so we have to look for the adjoint, right? So the adjoint, the adjoint, the adjoint of P will be equal to, you change the position of the main diagonal. This is the main diagonal. This is the main diagonal. You change the position of the main diagonal, and then you negate the off diagonal. the off diagonal is what goes this way, and the main diagonal is what goes that way. So here your adjoint becomes -4, 1, then you negate the off diagonal, and that becomes -1, -1. So once you have the adjoint and you have the determinant, you can find the inverse. So inverse of P is 1 over the determinant that of P times the adjoint of P, right? So here we are going to have 1 over -5, right? Times -4, -1, -1, +1, right? So this is basically equal to, when you spread the -1 on 5, you're going to have 4 on 5, 1 on 5, 1 on 5, and -1 on 5. So this becomes the inverse of P. Okay, so once we have the inverse of P, we can go ahead and obtain the D, right? Because we have our A, we have our P, we have our P inverse. So how do we get a D, right? The diagonal matrix. So let's go from here. Let me write the P somewhere here. So we have P to be 1, 1, 1, 4. Okay, so here our D is the eigenvalues. Okay, so eigenvalues has been given as 3 and -2. So the eigenvalues will position itself on the main diagonal, right? So the eigenvalues will position itself on the main diagonal, and the off diagonal will become zeros. Okay, so the D is 3, 0, 0, 2, because we have the eigenvalues to be 3 and -2. So this is the D, right? So first, we have to find the PD. Then we multiply the result with the P inverse. Okay, so we're going to have our PD. Now our P is 1, 1, 1, 4, and our D is 3, 0, 0, 2, right? So this, when you spread the first row with the first column, you're going to have 3 plus 0, then 0 plus -2, then we have 3 plus negative 3 plus 0, and then we have 1 times 0, that is 0, plus 8, right? So basically we are going to have our PD to be 3, 2, 3, and 8, right? So this is the result for the PD. This is the result for the PD. Okay, so once we have the PD, we can go ahead and multiply it with the inverse of P, and that is what we have right here. Okay, so let's do that computations. So PD times P inverse is going to be 3, 3, like 2 and 8. Then we have 4 on 5, 1 on 5, 1 on 5, like 1 on 5. So this is going to be the result for the PD times P inverse. Okay, so here 3 times 4 on 5, that is basically 12 on 5, plus negative 2 times 1 on 5, that is going to be negative 2 on 5. Then this first row again times the second column. So 3 times 1 on 5, that becomes 3 on 5. Then negative 2 times negative 1 on 5, that becomes plus 2 on 5, right? Then we take the second row, you take it, you take the second row, match it with the first column, and then the second column as well. So the first element will be 3 times 4 on 5, that's going to be 12 on 5. Then 3 times 1 on 5, 8 times 1 on 5 is going to be 8 on 5. Then 3 times 1 on 5 is going to be 3 on 5. 8 times 1 on 5, that is negative 1 on 5. Negative 8 on 5, right? So we do these computations very, very well. When we do these computations very, very well, we're going to have negative 12 on 5 minus 2 on 5 is basically 10 on 5, right? So we have 10 on 5. Then 3 on 5 plus 2 on 5 is basically 5 on 5. So we have 5 on 5. Then 12 on 5 plus 8 on 5, that is basically 20 on 5. So we have 20 on 5. And then 3 on 5 minus 8 on 5, that is basically minus 5 on 5. So we have minus 5 on 5, right? So this, when you simplify this, then you're going to have 10 on 5 is basically 2. 5 on 5 is basically 1. 20 on 5 is basically 4. Then minus 5 on 5 is basically minus 1, right? So this becomes our diagonal matrix. This becomes our diagonal matrix. Okay, so this result becomes our diagonal matrix. Since we have been able to successfully express A as PDP inverse, we confirm that A is indeed a diagonalizable matrix. So that's the diagonalizable matrix, or the diagonal matrix, is obtained as 3 2 3 0 0 2. That is this. Okay, so I told you that once you have been able to obtain successfully obtain the expressed A, right? Express A as PD P inverse, then you can say that D, right? D is indeed a diagonal matrix. So you can see the result over here. You can see the result. You can see the result that our PD, our PDP inverse is equal to 2 1 4 1, and that is the same as the matrix A, right? So once you obtain PDP inverse as A, the result is the same as matrix A or the matrix given, then you can say that D is indeed a diagonal matrix. So this becomes the diagonal matrix. Thus the diagonal matrix, the diagonal matrix is 3 0 0 2, right? The diagonal matrix is indeed 3 0 0 2. The diagonal matrix is basically the values of the eigenvalues, but we just want to confirm if indeed when you multiply the PD with the P inverse, you are going to have the matrix A. Ladies and gentlemen, thank you very much for watching. I really appreciate your time. Don't forget to subscribe, share with your mates, and I'll give you more updates. Bye-bye.